coming today and taking the attention. So A is so the differentials are for S over A.
Okay, so let's start again afternoon session. Let me introduce Hardouin, speaking about parametric genericity.
So I'd like to thank the organizer for the invitation. And I'd like to say that the results I will present today are really consequences of the beautiful theorem of classification of keys we all know about. In fact, thanks to this theorem, we can reduce the question of algebraic relation to a question of linear relation among functions, as Carlos has presented this morning. And I want to factor a similar result in the framework of Q-difference equation. So in my talk, I will be interested in functions like Z satisfying a certain type of functional equation, what we call Q-difference equation, which is a linear equation in a discrete operator that acts on the variable z by setting z to qz. So it's a discretization of the derivation in a certain sense. And my function will satisfy this kind of equation over C of z. I will only be concerned with rational coefficients. Okay, some examples of function fields endowed with this kind of discrete operator. So the first one is C of z, the field of rational function, endowed with the paradigm called sigma q, sense z of qz. And you can embed C of z in a larger field, the field of meromorphic function of a C star, endowed with the same operator. So it's an extension of difference. And these two fields have some discrete constants, that is, the element fixed by the operator. So for the rational function, it's a field of complex number, and for the field of meromorphic function of a C star, it's an elliptic function with respect to this following elliptic curve, which is written in a multiplicative way. So it's much larger constants. Some examples of Q functions. So the first one, which is one of the building blocks when we want to solve Q-difference equation, is the theta function. That is, in fact, in this case, the theta function of Jacobi. If you view it as a function of Q and Z, and you do some change of variable, so this theta function satisfies the following rank 1 Q-difference equation. So sigma q theta q equals qz theta q. And in my talk, I will be interested in the following special functions that are called Q hypergeometric series. I've called that power series expansion the following way. So this function satisfies the following Q-difference equation, which is in fact a discretization of the hypergeometric differential equation. And there is also some geometry behind this Q-difference equation, similar to the one for hypergeometric differential equation. It is more or less connected to discrete Gauss-Manin connection. So now, what can we ask about this Q function? We can ask about their complexity. So the first question will be, are they transcendental over the field of rational functions? That is, satisfy no algebraic relation. So this is the first in. And when they are transcendental, we want to say more about this function, and I will be interested in two different kinds of additional information. So the first one, I will call it hypertranscendental with respect to the derivation. That is, I will wonder if my Q function can satisfy a differential algebraic equation over C of Z. So such kind of information can be seen on an analytic point of view. For instance, if a function satisfies a linear differential equation, then we know that it's a regular function. It has only a finite number of singularities. And if I expand this function as a power series, I know how to control the growth of the coefficient. And I know also that the coefficient of this power series will satisfy some recurrence relation. So I have many kinds of information on an analytic point of view, on an algebraic point of view, and even we have seen with this Bushy theorem, it can be seen as in a model theoretic set. So what are the previous results in this direction? So as Michael exposed you this morning, we have this result of Ramis that tells you that a Q function that is also a power series that satisfies linear differential equation over COT must be a rational function. But one can find some hyperalgebraic Q function. So if you do this simple computation, you can see that, so with the derivation introduced this morning, d over dz commutes with sigma q. So just by playing with the functional equation in Q of the delta function, you find that the derivative of the log derivative of theta q is fixed by the operator sigma q. It means, since theta q is a meromorphic function over C star, that it is an elliptic function this time. You know that elliptic function can be written, in fact, as function in the Weierstrass and in the derivative of the variable function is in fact hyperalgebraic extension of C, and then you find that theta q is hyperalgebraic with C, but it's not a linear differential equation. So one would like to understand this kind of dependency. One could also ask for another kind of dependency. So if I take q prime, which is a fixed complex number that I take multiplicatively independent from q, I may wonder if my q function satisfies the sigma q prime relation over CRT. The similar results hold for linear equation. If a q function is a power series and satisfies the linear sigma q prime equation, then it must be a rational function. But once again, if I'm playing with the theta q function, I can find a non-linear sigma q prime relation for theta q. So I have some relation, but I cannot have linear one. So no, in order to answer to this kind of question with a systematic method, many parameterized Galois theory have been developed this recent year. So I just want to talk about the people that were involved in this theory. So now if I formalized with system, kind of question, so one can go from a linear sigma q equation to a system in the same manner that you go from a linear differential equation to order 1 differential equation. So I'm starting with a given matricial system, and I'm wondering about the differential or sigma q prime relation. So the first Galoisian approaches developed to this setting was done by Finis and Michael, where they were wondering about a differential system in X, say, and with a delta t relation for another derivation. We extended this setting with Michael to a certain amount of functional equation together with a continuous parameter, meaning the action of a parametric derivation. So this is this case. I have the sigma q equation, and I'm wondering about the differential relation. So if one would like to go to the discrete setting, discrete parameter, so one has to really do much more work and to develop a theory of difference group scheme that was mainly developed by Michael Wimmer, and in fact we extend the parameters Picard-Risso theory to the case of a discrete parameter. So now I will try to expose both settings in the case of two difference equations. But of course, I'm warning you, I will lie, because this discrete parameter setting is much more tricky than the continuous parameter one, because one cannot work with the point of the group, but with the defined parameter. So one has to have a schematic approach. So I will hide this, but you have to keep in mind that we are more focused in the defining equation of our objects than of their points. So I will use mainly two facts about difference equation. The first one is that I know where to solve them. So with the Picard-Vicious theory, most often to find solution one construct them in an algebraic way. We take a polynomial ring, we quotient via a difference ideal, and we find some abstract solution. In the Q-difference setting, we know that if we take a meromorphic matrix A, then we can solve every Q-difference system in the field of meromorphic function, which is very nice because most often with difference equations, one has to go to the ring setting. Having a field is for us an easier situation. Then, if I take another fundamental solution matrix of the same system, they will differ by a matrix of constants, matrix of elliptic function. So I have the control of the solution field and I have the control of the constants of this solution. Another kind of control I want to have is the control on the algebraic solution. When we are dealing with difference equation, big problem is passing to algebraic function because you have many choice of the extension of the difference operator, and this makes the theory of difference algebraic group really tricky. So I know that when I'm looking at the union of all the elliptic function, so not only respect with q but q to the r, and I'm considering this field of rational function with coefficient in this guy, both t, then it is relatively algebraically close in the field of meromorphic functions. So I know where are my algebraic solutions. So what I will do, in order not to have any problem, I will put all the algebraic guys in my base fields. So, no. If I go back to my initial problem, I take a matrix A of rational function, I solve it in the field of meromorphic function, and I denote by delta, the derivation, z over dc. So I'm interested in solving the system and deriving the solution, and of course, as in the usual setting, I don't want to add new constants. So, but now it is easy. I'm just taking the differential field generated by my solution inside the field of meromorphic function. Then there I know to derive solution, and I know that the constant of this guy is only the elliptic function, so I have the control on my constant. Then what I can see is my Li data is a sigma q of the field extension of my bed field. It's stable under sigma q and under the derivation. It's differentially generated by u over my best field, and it has no new constants. This such an object will be called a differential Picard-Vicious extension. So I'm changing a little bit the definition, but in fact, in order to define Galois group, it's more or less the best setting. So okay, and I can do the same trick with the sigma q prime operator. This time I am interested in the sigma q prime relation. I'm looking at the subfield generated by the fundamental solution matrix, and it's transformed with respect to sigma q prime, and I will find that it's a sigma q prime field extension, that is sigma q prime generated by the fundamental solution matrix, and it has no new constant. So I will call this object now a sigma q prime Picard-Vicious extension. Now that I have my splitting fields for both my problem, I can define the Picard-Vicious group. So, and now I am cheating a little bit because I will define it by the pointer, and I have decided to define this as a scheme, as a function, but let us stick to this definition. So I'm considering the field automorphism of my Picard-Vicious extension, stabilizing the base field, and commuting with the two operator I am interested. Then, as Carlos showed you this morning, the fundamental solution matrix is mapped to another one, so they must differ by a matrix of constants. That is, I find an embedding of my parameterized Galois group into the group, linear group with defined over CE. So the image of this group has some structure, and it appears that it is the CE points of a linear differential algebraic group scheme over the field of elliptic function. So that is more or less a matrix group scheme defined by differential algebraic equation over the elliptic function. So that is, I will be mainly interested by this defining algebraic equation. So the same kind of reasoning with the sigma q prime operator gives you, this time, you're looking at the automorphism that commutes with the operator you are interested in, so sigma qn, sigma q prime. The same kind of arguments give you faithful linear representation, but this time, the image of this representation is a sigma q prime differential algebraic group scheme. And in this setting, you are really obliged to look at the defining equation and not at their points in fields, because it's not sufficient, as Michael Wigner told you. So I will just quickly give you some examples. So the first one, so when I have this notation, this means that I'm looking at the linear group view as a scheme, in fact. So I'm taking an algebraic subgroup scheme defined over the elliptic function because it's defined by polynomial equation, it's also defined by differential polynomial equation, and it's a linear differential algebraic group scheme. Well, I can add a new equation. I mean, the equation that says that all the coefficients of the matrix are constants. So I have the polynomial algebraic equation of H and a new equation that of H equals 0. This defines me a linear differential algebraic group scheme over the field of elliptic function. And in fact, concerning linear differential algebraic group, these two examples will be the only one I will play with today. For difference algebraic group, it's more tricky. So you have, of course, any algebraic group will be a sigma q prime difference algebraic group for the same reason, but you have much more constant group, namely for each integer d, you can define the point of h that are stable under an iterate of sigma q prime, and there are linear sigma q prime difference algebraic group. So once again, these two examples will be the only one I will get in the follow. So now to go back to the classical setting, how do we go from the parameterized setting to the classical Figure-Vessel group? Well, you have your equation, you solve it in the field of meromorphic function, and then you just consider the field extension generated by the fundamental solution matrix. So it's then obvious that it's a field extension that solves the equation and that you have no new constant. So it's a classical Figure-Vessel field extension. If you look at the automorphism group of this field extension that commutes with sigma q, that can be in the same way embedded in the linear group defined with the CE, and it's an algebraic group scheme. Then Carlos told you, so this group is called Figure-Vessel group for the system, and Carlos told you this morning that it's Zariski dense, that the parameterized Galois group is Zariski dense in the usual Galois group. So you just imagine that you have one group defined by differential equation and the other by algebraic equation. So you throw away the differential equation, then you get the equation of the algebraic group. That's what the meaning of Zariski dense is. In the same manner, if you replace the parametric operator delta by the parametric operator sigma q prime, you find also that the parameterized group is Zariski dense in the usual Galois. So now I would like to just show you briefly. So we have a Galois correspondence in both of these settings. That mainly says that, so you have also to do some kind of schematic invariant, but once again, let's not talk about this. So the fixed point under the parametric Galois group lie in the base field. And this tells you the following. The defining equation for your parametric Galois group over the field of elliptic function are in one-to-one correspondence to the differential algebraic relation for the solution over the field C of C. So it's, so to say, a torso. The same thing holds for the discrete parameter. So now we have reduced the problem of this finding this extra relation by finding the defining equation of our Galois. So this is a very hard problem, and I would just say a little bit about this problem, the story of the problem. So we have a Q-difference system, and what do we know about the computation of this Galois group? So what's the classical Galois group that gives us the algebraic relation between the solution? So we have an algorithm 1 n equals 2 by entries, which is a kind of general algorithm. So Julien has, in fact, computed the Galois group of the hypergeometric Q-difference system of rank n. And we have a general algorithm by Hardouin, which has a lot of complexity. And well, it's more difficult to use. For parametric curvature group, so we know that it gives us differential or the sigma q prime algebraic relation between the solution. So we have general algorithm for parameterized differential equation by Andrei, Alexei, and Michael. And we have some complete algorithm for the rank 2. When I say complete, it means that we really have criteria on the coefficient of the equation. And we have criteria in terms being having a rational solution of an equation determined by the coefficient. So this is something one can really compute. Well, but for arbitrary system, there are almost nothing, I mean, really complete. So what I will expose now is what can we say when, in fact, as Carlos exposed this morning, when the group is large, the usual Galois group is large. What can we say about the parametrized Galois group? So I will just give you a first example. So let us consider a meromorphic solution of a rank 1 equation, where A of z is a non-zero rational function, and I take q prime multiplicatively independent from q. Then we know that either the parameterized Galois group is an OGM, that is, we have no relation, sigma q prime relation among the solution, or it is a subgroup of the sigma q prime algebraic. And the last condition is equivalent to the following thing. So if we are in this case, then A must be of the following form, which is also equivalent to the fact that I can find a rational function b of z such that sigma q prime of sigma q prime of u over u is equal to b of z sigma q prime of u over u. So just to emphasize what I was saying about the defining equation, so you have for the group this following defining equation, which gives you, in fact, the same equation for the solution, but this time over the base field. So now, what do we know about large PV group? And in fact, what can we say when we have some nice classification results? So for differential algebraic group, the following results hold. You take a K differentially closed field, and H a normal simple algebraic subgroup of G ln of K, G a proper Zariski-dense linear differential algebraic subgroup of H. Then this subgroup is conjugated to the group with constant differential entries. So this allows you to, in fact, goes from a purely algebraic setting to a linear one, as I will explain later. For different group scheme, you have to put some additional assumption. So one can work with an algebraic closed field because we are only considering scheme, but we need to assume that the subgroup, the sigma q prime subgroup, is sigma q prime integral. It means that it is given by a prime and reflexive ID, difference ID. Then we know that up to going to a field extension, we can conjugate our group to a group given by the equation sigma q prime d of g equal g. So this result is in fact an extension of a monotheoretic classification due to Zoïchatzidakis, Rushevsky, and Peters. So now this classification result translates to relation for the equation. So we have the first translation in for the differential parameter. So you're considering a Q-difference system and its classical Galois group H. We assume that H is an absolutely almost simple algebraic subgroup of GLLFC, let's say SLN. Then the following statements are equivalent. Either parameterized Galois group is as big as possible, it is H, or we have this integrable, differential integrable system that goes with the Q-difference system. And they are compatible. So compatible has two meanings that are equivalent. The first one is that we have this relation of compatibility, which is equivalent to the fact that I can solve these two systems with a fundamental solution matrix lying in some differential field extension. So this is equivalent, but one has to work to do the thesis. So we find similar results for the Q prime parameter. So I'm still assuming that my classical Galois group is an absolutely almost simple algebraic subgroup of GLN. Then I know that either my parameterized Picard-Vessier group is a full H, or I can complete my initial sigma Q system with a sigma Q prime system in the following way. So this theorem tells you that if you have some sigma Q prime algebraic relation among the solutions, then it must be linear relation. That's where we come to the theorem of Schenker-Zinka. Okay, so now the application to the Q function. So I'm taking a Q-difference equation or its companion system. And we have the following. So let G, subgroup of GLLFC, the Picard-Vessier group of system, so over C. And we can do some comparison between the subgroup, the Picard-Vessier group over C and the Picard-Vessier group over the elliptic function. And let's F, sigma Q n minus 1 of F, be a non-zero solution vector. So we assume that the connected component of the group of commutator of G is either SLN or SPN or SON. So it depends on N. Then the following holds. So the parameterized Galois group contains SLN or SPN or SON, and which tells us that we have the following hypertranscendence results. So we are not in the degenerate case. And the same kind of result holds for the discrete parameter. So if you have the same assumption on the classical Galois group, its derived connected component is either SLN or PN or SON. then a solution of your equation is always sigma q prime transcendental over the base. So we were able to apply this theorem to Qi hypergeometric series. So we consider a Qi hypergeometric function. So we take, I don't know if you remember, the same, here the same n, and we assume that our Q difference equation is irreducible, and then we have this combinatorial property. Then, under this assumption, in fact, Genericity was able to say that the usual Galois group contains SLN or SPN or SLN. And we find that the Q hypergeometric function is sigma Q prime transcendent and differentially transcendent. So I will recap you, in fact, the ingredients of such kind of proof. So you are starting with your functional initial system, which is a Q difference one, and you assume that its usual Galois group equals SLN. Let's make simple. Then after it's a little bit more complicated to go to this projective isomodulatomy Carlos was talking about. So let's just make it simple. Let's say it's SLN. So I'm considering a non-zero solution that is lying in the field of of Laurent series in some ramification of the variable. I can do this, in fact, by looking more closely at the form of the matrix. Then the ingredients of our proof are the first one. So we take some comparison results for classical Q difference group over C and over the elliptic function. And now we have this integrability result that told us that if the parameterized Galois group is not a SLN, then the system is compatible. And the last ingredient is, this famous result initially, that if you have a power series solution of a linear differential equation and a linear Q difference equation, then G must be a rational function. So we have to work a little bit to say that if I take a solution of this system, then it satisfies also a linear equation, but it's a small amount of work than when we have the compatible pair of equation. Then you see the vector, the solution vector G of the, sorry, it should be a sigma Q n minus 1 of G is the solution vector with entry in the field of rational function. Well, then it's fixed by the Galois group, because the Galois group fixed the base field. But the Galois group is SLN. So we find a contradiction. So that's, mainly the basic idea of all these proofs. Of course, there are some technicalities to go to this equal SLN to contain SLN, and also to work through the form of the solution. But I hope I gave you this 3 steps that, in fact, as Carlos told you this morning, works in many different settings, when you know that the 2 operators you are considering are independent. So, thank you.
Are there questions, comments?
I'm curious. So you gave results about the this generalized Q hypergeometric function with NN values. What do you know about the ones where the numbers aren't equal? I mean, do you still know, for example, what the classical Galois group for them is?
Yes. It's also classified.
But you just don't know that it's one of these SPN or SLN in order to.
Yeah, it's mainly Julien work. I don't know all the details. I think you
Yes.
classify.
Yes, I wrote a paper on this.
Oh, okay.
And
yes.
yes, you have the same kind of results. So you can compute the Galois groups in many cases, and you find in most cases SLM actually. Something which is between SLM and GLM.
Other questions? Well, thank you. So we'll start in 10 minutes. Yeah, 10 minutes.